सेटिंग पहले ही रखनी चाहिए। टास्क रिवर्ट करते हैं तो
समझी थी 2:30 बजे।
नहीं 2 बजे
10 मिनट पहले आके करते, मैं भूल गई थी। ओके
वापस कहाँ से जाना है? अच्छा जी, मैं अब हम तैयार हैं इसको स्टार्ट करने के लिए। बिफोर मैं फॉर्मली इसको स्टार्ट करूं, मैं उर्दू में अनाउंसमेंट करना चाहता हूं कि पिछली दफ़ा भी हमें जी बहुत प्रॉब्लम हुई है इसकी वजह से, और काइंडली इस दफ़ा हैव सम कंपैशन ऑन अस। हमारा जो जॉब है उसको आसान रखिए और हमें मुश्किल में ना डालें। और फिर स्पीकर को भी प्रॉब्लम होती है, मुझे बार बार अनाउंसमेंट करनी पड़ती है और फिर स्पीकर को उनका फ्लो भी टूट जाता है। लेकिन जी हर हालत में आपने अपनी वीडियो ऑन रखनी है। ये कोई एक्सक्यूज नहीं चलेगी कि जी आपके पास इस वक्त इंटरनेट ठीक नहीं है और ये चीज है। ये एक रूल है जो PEC ने हमारे पे लगाया हुआ है। और अगर हम ऐसे शख्स को सर्टिफिकेट दे दें CPD तो हमारा लाइसेंस ज़ाया हो सकता है। तो इसलिए काइंडली इस पे हम कोई गुंजाइश नहीं दे सकते। आपने अपनी वीडियो ऑन रखनी है, ये आपकी जिम्मेदारी है कैसे रखनी है। इस वजह से कि जी नेट ठीक नहीं है या मेरे कोई सिस्टम में प्रॉब्लम आ रही है, इस पे मैं कोई गुंजाइश आप लोगों को नहीं दे सकता। तो इसलिए हमें भी ना मुश्किल में डालें और अपने आप को भी मुश्किल में ना डालें। काइंडली अपनी वीडियो आपने ऑन रखनी है हर हालत में। थैंक यू जी, शुक्रिया। बिस्मिल्लाहिर्रहमानिर्रहीम। Assalamu alaikum, ladies and gentlemen. I welcome all of you to our 23rd lecture of Pakistan Society of Civil Engineers. Today's speaker is Dr. Fawad Muzaffar. He is delivering his lecture second time from this platform, and today's topic is design of buildings. Now, today's lecture time would be approximately 2 hours. And one clarification, Dr. Saab, would you allow questions during the lecture, or would you prefer the questions should be asked at the end of the lecture during the Q&A time?
But I think I'd like to finish it up in 1.5 hours, because I have more stuff than 1.5 hours. So whatever I can cover, I'll finish it up in 1.5 hours. And after that, we can have a 30-minute or more, if you like, question answer session. But if we do it interactively during an online meeting, it might be not that manageable. So, but it's up to you.
We always follow the priority set by the speaker. So, ladies and gentlemen, you have already listened to Dr. Fawad. He would prefer that the question should be asked at the end. But if you have any questions during the lecture, kindly keep on sending through text. I will note down all the questions, and at the end, then I will I will read out the questions to Dr. Saab, and Dr. Saab will be pleased to answer your questions. So no interruption for the questions during the lecture. So again, as Dr. Saab has said, the questions, the lecture time would be 1.5 hours, and at the end, 20 to 30 minutes would be allocated for question answers. Regarding video, now I am making a formal announcement. As per rules set out by Pakistan Engineering Council, every participant who is aspiring for the CPD certificate, he has to keep his video on. His face should appear live on the screen. Thank you. Now, introduction of Dr. Saab. Doctor, as I said, this is the second time Dr. Saab is appearing on our platform, and he has done his bachelor's in civil and environmental engineering from UET Lahore in 2000. Then he proceeded to Stanford University, California in 2004 for his master's and PhD. Alhamdulillah, he is a PhD, and he is okay. after doing his bachelor's, he has worked as a site engineer on number of projects here and there, and one of them was the Gadi Shahu Bridge, where he was most probably he worked as a supervisor engineer. He joined NESPARC in 2001, and he worked on number of projects in NESPARC related to design and vetting of the design. His main, the structures he designed related to transportation, pre-stressed bridges, and the projects he handled was N70, a highway, Islamabad Murree dual carriageway, and some other projects. Currently, he is the general manager in Infrastructure Development Authority of Punjab, IDEP, general manager engineering and planning in Infrastructure Development Authority Punjab, abbreviated as IDAP. And here he has been working again on design and vetting of the projects. He is designing the projects himself, and in some cases he's vetting. And these projects are High, Q Tower, City Shopping Mall, Sky Park, Pakistan Kidney and Liver Institute, and many other projects. So this was a very brief introduction of Dr. Saab. He must have, I don't have the details of his publication, must have some publications also. And he's quite a learned engineer and highly reputed in Pakistan. And I'm pretty sure that today's lecture, design of buildings, would be full of knowledge. And I'm pretty sure you will have ample opportunity to learn from this lecture. Thank you very much, Dr. Saab. Please go ahead. The floor is yours.
Thank you very much, sir. Thank you for the introduction. Nice to have everyone who's listening to the lecture. I have, as I said, I have a lot of material, but I'll try to cover as much as I can in 1.5 hours. And the intent is not to give you an in-depth understanding of the basics of in-depth understanding of the the rationale and the engineering behind the new codes, but it is just to give you a flavor, a brief flavor of what it is that they are doing, how the codes are evolving, and what is the engineering behind it. So I don't know if I can share my screen already. Can you enable me to share my screen?
Just a minute, Ji, I will do it. Just a minute. Give me a second. There you go. You are all set to share your screen. Please.
Okay. So let me share my screen with you guys. So I hope you can see the presentation. Can everyone, Tahir Sahab, can you see my presentation?
Very well, Ji. Thank you. Aa gayi hai.
Okay. Now probably you guys can see my screen.
Ji, aapki screen clear hai? Please go ahead.
Can you see the presentation now?
Yes,
okay.
Very clearly.
So with the assumption that everyone can, okay. So with the assumption that everyone can see the presentation, let's start. I did this last year. I don't know if all of you were happened to listen to my lecture last year. So I'll give you a brief as to the state of practice in Pakistan. Then from that point on, I'll contrast it with whatever is happening recently. Internationally, I will bring out all the differences, and then I'll try to give you a brief of the seismic, how the seismic hazard is characterized, and how we should be cognizant of the, the basic, very basic working of what goes on behind that response spectrum that you use to design the buildings. So let me start with the state of practice in Pakistan. You know, typically once we start a project, we have the topographic survey done. So we have a fair bit of idea as to what the landscape looks like, followed by geotechnical investigation, which typically involves execution of a number of boreholes and you know, the SPTs and different types of soil and water tests that are done on the soil. After that, you know, typically the structural engineer would select a flooring system, which is most often in urban areas. It is a flat slab or a flat plate, or a beam slab system. Rarely, for larger spans, we go for waffle or other systems. You know, after that, the structural engineer selects lateral force resisting system. Two of these lateral force resisting systems are very common. The first one is dual system that everyone seems to use, and the second one is the, you know, the special moment resisting frame system or the intermediate moment resisting frame systems. Very rarely do people use other systems, except maybe bearing wall systems in some cases, where you would like to have just the walls of the building support the lateral force of the that is to be imposed on the building. After that, the structural engineer comes and he selects the live and dead loads. People use UBC 97. Some people use ASCE 716 because UBC 97 does not contain that that list of different types of gravity loads that is there in ASCE 716 or ASCE 710 or earlier ASCE. After that, you know, as far as the seismic loads are concerned, you just have this zonation done in the UBC 97, or which we call Pakistan Building Code, and from this we pick a particular zone. Basically, what we are doing is we are assuming that a certain PGA is associated with each of these zones, and then we build the response spectrum accordingly. After that, you know, the base shear is calculated from the standard formulas: V is equal to CV over T, I over R into W. These are the same, you know, the coefficients that are used to construct the response spectrum. And at the end of the day, a response spectrum is constructed for the seismic load of the building. The structural engineer also looks into the different types of irregularities that might be there, the vertical irregularity and the structural irregularities. Everyone knows how to use an ETABS model, right? Even people who have just graduated out of college know how to make a ETABS model. A linear elastic analysis is then carried out using the ETABS model. Based on the force demands from the linear elastic structural analysis, the sorry, Riyaz sir, can you mute your mic, please? Thank you.
Dr. Saab, just a second. I want to make one announcement. With those who have not switched on their cameras, their video, I'm requesting last time that they should switch on their video. If you are not appearing live on the screen, we will not issue you the certificates. This is the last announcement, and now I will not announce it again. Second, I request all of you to keep your microphones in mute positions. We are getting a lot of humming sounds from the background. Keep your microphone in mute position and let the speaker deliver his lecture uninterrupted. Thank you very much.
Okay. So after, based on it, The structural engineer goes on and starts and carries out the structural design. After that, the foundation of the structure is designed, computer, and a separate computer model is typically built to design the foundation of the building. Now, this is very important, because a separate computer model is safe or another software is constructed out of it. And this is, I'll come back to it later, but this is very important because what you are doing by doing this is you are constructing two different models which do not have deformation compatibility with each other. And lastly, the foundations are designed based on the analysis of the model and the the calculations of the structural engineer. So this is what everyone knows how to do in Pakistan. This is very typical. This is not rocket science. Everyone knows how to do it. But let me take you guys gradually towards whatever is happening internationally. So I'll start off with seismic hazard characterization. That response spectrum that everyone tends to use. What is the background of it? From where did it come from? And the answer is seismic hazard characterization. What does it? What do we mean by that? Well, let me start off by showing you an actual simulation of different seismometers that have been installed across the US and how they record each and every event around the world. This is just one of the simulations, right? So what they have done is they have installed hundreds and if not thousands of these seismometers across the US. And every time there's an earthquake, all of those instruments record the acceleration ground history of the event. Now, over a passage of time, over like decades, they have been able to accumulate a lot of these ground motion acceleration histories, right? So from these ground motion acceleration histories, what they have done is they have empirically calibrated different ground motion parameters. So now what are the ground motion parameters? The ground motion parameters can be the peak acceleration of the ground, which is called PGA. It's most commonly known by everyone. It can be PGD, peak ground displacement, or it can be PGV, peak ground velocity. But by far, the most common ground motion parameter that interests everyone is the PGA, the peak ground acceleration. So what they did was, or what they noticed was that if they plotted different, if they took out the peak ground acceleration of each of those measurements and they plotted it against the distance from the source, they would get a scatter that is shown to you in the form of these yellow dots. And statistically speaking, they could then fit a mean curve and see as to what the distribution of the different events around that mean value is, which they found out to be normal distribution. So this sort of relationship is basically a relationship between the distance of a certain point from the source of the earthquake. And as you can see, as the distance increases from the source, the line, the ground parameter of interest, the PGA, decreases. These relationships are called attenuation relationships. Okay, so for each one of those events that you see each one of those stations where the ground motion history is recorded, they plotted all of the scatter, fitted a mean to it, and then calculated as to what the distribution around that mean for a certain distance is. And it came out to be a normal distribution. ठीक है जी. Now there are two types of seismic hazard analysis. The original seismic hazard analysis that they used to do in 1970s and 60s was the deterministic seismic hazard analysis. And basically what that analysis is, that if you have a site, then you can have multiple sources of a hazard around that site. Those sources can be point sources, for example, volcanoes. Those sources can be line sources, meaning they can be faults, or those sources can be area sources where we do not have a well-defined source of the earthquake, but it's assumed to be spread around a certain area. Now, remember those attenuation relationships, what they did was they gave you the ground motion parameter as a function of the distance from the source. So if, for example, we have a site and it has source 1, source 2, and source 3 around that, right? We can then determine the minimum distance from the source to the site for each one of those sources. And then we can plot those statistical means, i.e. the attenuation relationships, and get 3 curves for each of the sources like this. And then we can basically see that one of the sources would be affecting the site the most. That source is called the control source, and that earthquake is called the controlled earthquake. Basically what we are saying is we are not concerned with the other 2 sources. We are just taking the source that is most likely to affect the site. Now this source is called so this process of development of attenuation relationships and then identifying the source from the site is called deterministic seismic hazard analysis. But it has 2 major drawbacks. The deterministic seismic hazard analysis only deals with the possibility of an earthquake and not the likelihood. What that means is, I'm saying, give me the worst case scenario for which I should design my structure which is located at that site. What do I mean by that? I mean, first of all, what it means is, I have calculated the minimum distance from the source to the site. I have not taken into consideration the fact that earthquake can happen anywhere along the within the source, right? Similarly, I have assumed that for in each source, the magnitude of the earthquake will be maximum. So basically, I have not considered that the source will be producing earthquakes of lesser magnitude. So this was done in the 1950s, 60s, and this method or this approach is called the deterministic seismic hazard analysis. But lately, people realize its limitation, which is it deals with within the realm of possibility and not within the realm of likelihood. Now, subsequently, they developed an approach which is called probabilistic seismic hazard analysis. And this approach basically not only takes into account the fact that earthquake can happen anywhere within the source, that magnitude of the earthquake can be anywhere from magnitude 4 all the way up to magnitude 9 or maybe 10, that the intensity of the ground motion at site is also not certain for a certain magnitude and certain distance from the source. And furthermore, we do not know when the earthquake will occur. So the probabilistic seismic hazard analysis basically takes into account all of these uncertainties. It does not take into account the worst case scenario. Now, then they discovered, as I told you before, that there are different types of sources. There are point sources. For example, there is an example of point source. There can be line sources, faults, like the main boundary thrust in Pakistan is a line source. Area source is basically you can have you can have an area and you do not know as to where the earthquake will occur, and that is you typically the case where the fault lines are not well established. So there are three types of area sources that they discovered. I will not take you deeper into this because I don't think you guys will understand it. But basically, what they said was for a line source, it is equally likely that the earthquake will happen anywhere along the line, as you can see in the figure B. And for an area source, they divided it into different grids and basically said that it is equally likely that the earthquake will happen within one of those grids. The next question was how big the earthquake will be. There are three types of laws that they used. The slip dependent laws, which is basically applicable for sources that have a well-defined slip rate. The Gutenberg-Richter laws, which basically describes that the number of earthquakes occurring annually from a given source is a log linear function of magnitude. And lastly, they realized that from a certain source, you cannot have earthquakes greater than a certain, higher than a certain magnitude. And basically, this characteristic equation, earthquake recurrence laws, is an adaptation of the previous Gutenberg-Richter recurrence law with the taper off of the maximum line that you can see here. And this is typically taken from the geological data. And they did the temporal uncertainty by using the Poisson's model, which is basically, they assume that there is an equal likelihood of an event or an earthquake happening within a certain magnitude, within a certain period of time, or for a certain unit time. Now, and then because all of those things were, different probabilities, they stitched everything together using the total probability theorem, and basically came up with this big equation. Now, remember the scatter that I told you? If you can see the figure, you can see that there is a normal distribution associated with every point on this curve about the mean, right? So after doing all of the probabilistic stuff, and I'll not take you deeper into it because I don't want to lose your attention, they developed a seismic hazard curve, the solid black curve that you see on the top there. Now, basically what that curve is giving you is annual frequency of exceedance, or in other words, what this curve is giving you is a relationship between probability of a certain magnitude of earthquake happening per year with the PGA, right? So if the x-axis is the peak ground acceleration, whereas the y-axis is the annual frequency of exceedance, right? So annual frequency of exceedance is basically the mean number of expected earthquakes of certain magnitude that we expect to happen in a particular year. So from these seismic hazard curve, what they generated was the uniform hazard curve. What the uniform hazard curve, and how did they do it? Basically, what we are interested in is, for example, what is the uniform hazard curve for an event that we expect to happen every 50 years, for example, right? So we would have this horizontal line here, and from that horizontal line, we can have these different intercepts with the different, the time period of the oscillators for the different ground motions. And then from these intercepts, we can read the spectral acceleration and, similarly plot those spectral accelerations as a function of the time period of the oscillators. And if we do that, we get something like this. Now this is too much for you guys, but I just wanted to give you a flavor. Now, from those types of analysis, they generated these different contours. What are those contours? If you look at the contour on the right, this is basically what this is showing. This is the region that this is covering is basically northern Pakistan, right? And I took it from a PhD thesis. The contours show you that, for example, the point, if you can see my cursor, a 0.8 PGA earthquake with the probability of happening with a of, for example, after every 2,475 years is this line. So what this means is the probability, if you follow this line, I would expect that an earthquake will happen every 2,475 years. And as a result of that earthquake, my peak ground acceleration will be 0.8. Okay. So similarly, sometimes they draw these contours, the other times they have these fancy colors on the left. This exercise has been done for the whole of the world, and you can download these maps from the Global Seismic Hazard Analysis Program website. And basically they have done it for different return periods. What I mean is this map will be changed for different return periods. So this one is for, I think, 2,475 years, which is the MCER level for the UBC 97. Just a quick overview of the tectonic setting of Pakistan. This is all of the faults that are going from northeast to southwest are strike slip faults. And in general, all of the faults that are perpendicular to it are reverse faults or thrust faults. And you can see that the fault on the left is basically the Chaman fault here. This is the Salt Range fault, and the Kalabagh fault, and then you see the main boundary thrust, arcing from southeast to or arcing like this. I don't know if you can see my cursor, but basically what I'm talking about is the fault number 3. If you can see the screen also. Some more of the fault tectonic setting of Pakistan. Now this is actually taken. I just wanted to sensitize you guys as to where should we expect the next big one. And there is that concept in seismologists call it the seismic gap. Basically, what we know is that between the Tibetan plateau and the Indian boundary, there is an arc, right? And that arc is basically the main boundary thrust. This is a reverse thrust fault. And so we know the source, and we know that that fault will be slipping under the Eurasian plate or the Tibetan plate. And on average, whenever there is a lack of event, that is the place where we should expect the next one. And if you look at it, just northeast of Islamabad, the last big earthquake happened in 1555. So this is like centuries ago, this earthquake happened. And now we should expect an earthquake in this region. Similarly, there was no event recorded, north of Delhi. And this sort of thing is called seismic gap. And seismologists tell us that within these seismic gaps, we should expect the next big earthquakes. So, we have one in Kabul in 1842. The 2005 earthquake is also marked here. But the next big one should be northeast of Islamabad or northwest of Islamabad, and it's due. So with all of this I'm sure most of you will be bored. With all of this background, there's a lot of science, there's a lot of seismology that has gone into it. I'd like to now introduce you to as to how things have evolved since UBC 97 was adopted. There are so this actually slide shows a very brief overview of how Codal stipulations are formulated in the US. What they have is a Building Seismic Safety Council, and basically that's a council where a lot of experts they meet, and they talk about important problems facing the construction industry. They identify the key problems and the research behind it and send it to NERUP, which is the National Earthquake Hazard Reduction Program. NERUP then further discusses those recommendations and the research, and then stipulates the Codal, the Codal, what do you call it? The Codal provisions. And NERUP then send it to the American Society of Civil Engineers, which then adopt those after review. After the provisions have been adopted in ASCE, they send it to the IBC, which then reviews and adopts it. And this is basically the hierarchy of different Codal stipulations. Now, if you open ASCE 716, you will see contour maps like the ones that I showed you a few slides back. Now you know from where these contour maps come, right? It comes from probabilistic seismic hazard analysis and all that probabilistic stuff. So the first thing that an American engineer would do would be to locate his structure on the map and read values of SS and S1. SS and S1 are spectral accelerations at 0.2 seconds and 1 second, right? After that, the engineer goes in and he basically looks at the uses either the crossfall survey or the SPT blow counts to classify his soil at the site. This is similar to what we do in UBC 97, right? But then he adopts these FA and FV coefficients. Basically, what these coefficients are, the ground motions that we discussed, the spectral accelerations that I showed you. Let me take you back. I'm trying to do that. Yeah, the spectral accelerations that are mapped here in the ASCE 716 are accelerations of the rock, and basically, there's a lot of soil on top of the rocks typically, and that soil can either amplify or de-amplify all of those accelerations. So FA and FV are basically coefficients that take into account those variations. I'm actually struggling with. Okay, and basically another way to, and I'm not taking to the simulation here, but the engineer then calculates SMS and SM1 by multiplying the FA and FV coefficients with the SS and S1 that we have that are mapped in the ASCE 716. From those SMS and SM1s, the engineer calculates SD1 and SDS by simply scaling it with a fudge factor of 2/3. This fudge factor, there's not much science to it, because it's a fudge factor. Because what they ended up with in ASCE 716 is that the ground motions were a lot higher as compared to what they were using, and they didn't want to change all of the buildings, or they didn't want to outdate all of the buildings. So they basically figured out that a factor of 2/3 should be sufficient to make it compatible with the previous codes, and that's from where this fudge factor comes in. And after that, the engineer constructs the response spectrum. But there are so the overall process is the same, right? But there are marked differences between ASCE 716 and UBC 97. First of all, the prescribed lateral force resisting systems have expanded a lot. So, in UBC 97, you would have only a few types of bearing wall systems, but in ASCE 716, you have a lot of them, right? So similarly is the case with building frame systems. You have a lot more of these building frame systems as compared to the systems in UBC 97. But something new is also included. I mean, most of us are accustomed to using dual systems. And in dual systems, if you open up ASCE UBC 97, you would not be able to use an special. There's no prescription of value of R for special moment resisting frame. Special shear wall with intermediate moment resisting frame. So if you open UBC 97, you don't have that system. But here they have included, the dual system with intermediate moment frames capable of resisting at least 25% of prescribed shear force, and they have coupled it up with special reinforced concrete shear walls, as you can see in paragraph E2. So there are a lot of new building frame systems. Secondly, one other big difference that we have, and I'm struggling with my computer, is this coefficient deflection amplification factor CD. So in UBC 97, you are told that an overstrength factor or response modification coefficient of R is given, and we are told that to convert an elastic deformation into an inelastic deformation when it comes to drift, we just have to multiply it with 0.7 R, right? And it's a fudge factor. But here they have included deflection amplification factor separately and response modification coefficient or overstrength factor R separately. So these two are now decoupled in the new codes. One of the key differences, and the world has moved on, one of the key differences is if you use UBC 97 to design a building, there is a 10% probability that your ground motion will be exceeded in the next 50 years. Now, this is unacceptable by international standards, whereas in the ASCE 716, even in the IBC code, now there's a 2%, they have ramped up the ground motions. So now there is a 2% probability that your ground motion will be exceeded in the next 50 years, which is a lot less as compared to 10% probability of exceedance. Now, this has a lot of repercussions. All of the buildings that you're designing in Pakistan are basically are basically obsolete as far as the new standards are concerned. See, I was talking to you about how to calculate the maximum inelastic response to displacement. On the left side, you see UBC specifies 0.7 R delta S, right? And to calculate delta S, UBC tells you that you should use the base shear that you use to calculate force effects. Correct me if I'm wrong, but this is what I understand from UBC 97. On the other hand, in ASCE 716, they give you this CD factor in the tables, and this delta max is basically analogous to this delta S, the interstory drift that you get from your linear elastic analysis. Also note that they have divided the importance fact. They have divided this these delta max with the IE. So basically, the importance factor is in the denominator. It's no longer going to affect your interstory drifts. So the way you calculate interstory drifts in ASCE 716 is completely different from UBC 97. Although the restrictions on interstory drift are much tougher. So UBC 97 tells you that for a building whose time period is less than 0.7 seconds, your H over L should be equal to 0.025, and it should be equal to 0.02 for buildings whose time period is greater than 0.7. On the other hand, if you look at ASCE 716, these ratios are much more stricter. So it's and it is based on risk category of the building. It's no longer independent of the risk category of the building. So for risk category 3, for example, it is 0.015, which is if you have a building whose time period is less than 0.7 second, it is 0.025. So in certain cases, the interstory drift is much more stricter as compared to that of the interstory drift of the UBC 97. Although this equation 12.1, which uses the CD factor, is much more relaxed as compared to the previous case. Then equation 34 on the left side is used to calculate the Bayer, whereas they have changed the equation in the new codes, which is previously it was V is equal to CV over TI over R into W, whereas in this code it is V is equal to CSW. And CS basically is calculated using a bunch of these equations. Importance factor. In UBC 97, the importance factor is basically related to the type of the occupancy of the building. So for essential facilities, the seismic importance factor will be 1.25. For hazardous building is 1.25, and for special occupancy structure is 1. On the other hand, in ASCE 716, basically what they tell you is the importance factor is related to the risk category of the building. Now, what is the risk category of the building? The risk category of the building is basically dependent on the number of persons whose life will be at risk if the building collapses. Now, this is not the number of persons. These are not the number of persons who will die, who will be inside and who will die because of the collapse of the building. These are the number of persons whose life can be affected. So they, for example, if you consider a hospital, it might be housing 50, 60, or maybe 100 people. But all the people that the hospital is serving is basically also counted towards the number of people who will be affected if the hospital collapses. Now, so from that, from this chart, we figure out, if you look at the table on the right side, we figure out the risk category of the building, and the importance factor changes as per the risk category of the building. So the importance factor is no longer solely dependent on the occupancy of the intended use of the building. It is a function of the number of people whose life will be affected. And this is a very big change. Now in UBC 97, to calculate the fundamental time period, you use T is equal to CT H raised to 3 over 4, right? Or you can use method B, which basically tells you that you can ramp up this time period with a factor of 1.4, right? In ASCE 716, in the last decade or so, what they have realized is that the time period is basically overestimated. In most of the cases, if you are using your finite element software to calculate the first mode and fundamental time period, it will overestimate the time period, and that will result in reduction of your base shape. So basically what they have done is they have prescribed to use this equation T is equal to CT HX raised to n, but they have limited the upper bound. They put up cap on the time period, and what they've said is, limit this time period that you obtain from equation 12.87 to by using this coefficient CU obtained from 12.81, table 12.81, and there is this plot that they provide in the commentary section. Basically, each point on this plot is the time period that analysis of the structure and versus the actual time period. And you see that the lines, the black lines that you see in this plot are the predictions of or the upper bound cap of the the lower bound cap of the time period of the structure. So they have put much more the restriction on the upper bound of the time period is much more stricter as compared to previous. So with these major differences between the ASCE 716 and UBC 97, I'd like to actually take you back as to if you're using the building code of Pakistan to design a building, I would say that it is no longer safe. So the first thing that I'll point you, or the first evidence that I will point you towards is building code for Pakistan is based on UBC 97. If you look into UBC 97 for Pakistan, Islamabad and Karachi, Peshawar are zone 4, whereas Lahore is zone 2A. On the other hand, in building code of Pakistan, Karachi is zone 2B and Islamabad is zone 2B. So if you are designing something in Islamabad based on building code of Pakistan, you're grossly underestimating the seismic hazard. Even in the OBO supplement IPC 2015, which is basically an American supplemental code that they issued IPC 2015, you can see that they have put Islamabad in zone 4 and Karachi in zone 3. So it is by no means one-off that they have overestimated UBC 97. They're consistently telling you that Karachi and Islamabad are much higher seismic zones as compared to building code of Pakistan. The next evidence that I present to you guys is I started to take a look at it for Lahore, and there is an Indian code that they have developed using the probabilistic seismic hazard analysis, and basically, it would be. I thought to myself that it would be very interesting to compare the PGAs of, for example, Lahore and Amritsar, because both of those regions are located adjacent to each other, and the seismic hazard should be the same. So on the left side, you see the seismic zonation of India. On the right side, you see the seismic zonation of Pakistan as contained in the building code of Pakistan. These are some more slides from the Indian code, which you probably cannot download because they have blocked every IP from that goes from Pakistan. And then these are more slides. They have specified R vectors for the different structures, the Indian codes. What we did in our design office is we plotted different response spectrums for Lahore, for Islamabad, using different codes. The building code of Pakistan in the orange is the lowermost. The UBC response spectrum, the UBC 97, the original, the zone 4 is the green one, which is the middle one. And the IBC response spectrum, IBC OBO response spectrum is the blue one. You can see that the Pakistan building code response spectrum is nowhere near the UBC response spectrum or the 2015 OBO code response spectrum in blue. It is grossly overestimated. It grossly overestimates the seismic hazard of Islamabad. Then, we constructed the response spectrum of Lahore in IDAP, we constructed the response spectrum of Lahore using Indian code. Sorry, Amritsar using Indian code, and we compared it with the response spectrum that we use in Lahore, for Lahore as per UBC 97. And this is how the comparison looks like. Now, I don't think that it is very different, even at higher natural time periods. The base shears, as per the 3 codes, we computed it for one of the buildings that we were doing. The UBC base shear is approximately 1.5, 1.6 times the building code of Pakistan base shear, and the IBC base shear is even more than the UBC response, the UBC base shear. And lastly, I think because I've covered a lot of stuff, and I'm pretty much out of energy here. Most of us who are practicing structural engineering resort to response spectrum analysis, right, to calculate interstory drifts. But what you don't realize is that if you carry out response spectrum analysis, you lose directionality. So I taken this page out of Ghosh's book, and basically what that is telling us is you don't know the shape of the modes when you are combining those modes to get the final deflected shape. The modes can be opposing each other, the modes can be complementing each other, but we don't know that because the inherent nature of the response spectrum analysis is that it basically we lose directionality. So you should be careful as to what you look at using ETABS. Whereas ETABS does this, ETABS basically uses all of the modes, takes all of the modes and calculates the response spectrum based on one direction and another direction, and then gives you the critical value. But if you are using another software, you should be aware of this fact that you should not be able to mix different response spectrum, the different response, the different modes, that are out of phase with each other, and erroneously predict an interstory drift. All right, so I don't think I'll take you to the ground motion selection, maybe next year, but not this year, definitely. And so I just wanted to present to you different things that we arbitrarily have realized in our design practice, and we take those things into account. One of those things is basically seismic hazard, how we deal with it. The other thing is we use modern codes. We no longer use UBC 97. We tend to use ASCE 716 more and more. We are cognizant of the fact that the seismic zonation of Pakistan is not ideally done. It should be dealt with more thoroughly and all that. So with this, I think I'll open the floor for questions. I understand I went through a lot of stuff. I've spent last night, probably I slept at 2, so I'm pretty much out of energy. And if you guys want to have an interactive session, fine. If you have any questions, I'll open the floor.
Dr. Saab, there are some questions, and I'm going to read out those questions for you.
Sure.
Can you hear me?
Gigi, I can, sure, sir.
The first question is from Mr. Furqan Hamid. He is asking, is relationship with depth of seismic source to site is analyzed too? Which earthquake magnitude will be taken into consideration, qualitative or quantitative for building design?
Sorry, Tahir Sahab, आपकी आवाज कट गई थी. Can you please? Whatever I heard is he's asking for if the depth of the seismic source is also a factor in attenuation functions.
Yeah, I think he's asking what you have understood. I will read the question again. Is a relationship with depth of seismic source to site is analyzed to one? And second is, I think, asking which earthquake magnitude will be taken into consideration, qualitative or quantitative, for building design?
So the answer to the first question is what he's asking rightly. What he's pointing towards is hypocenter and epicenter. Yes, we use hypocenter. Hypocenter is basically the location of the earthquake at that point. Along with it's not the epicenter is the projection of the source of earthquake to the surface. So yeah, the short answer to his question is we do take into account the depth of the event when we are analyzing or developing the attenuation functions. The answer to the second question is we do. I don't understand what he means by qualitative and quantitative, but we do consider the magnitude of the earthquake, all of those in the probabilistic framework that I've just discussed. So we do consider different magnitude of the earthquakes, and typically those magnitude of the earthquakes are very discrete points. They are not continuous. So there objectively there are a few points that we consider which are available from historical data. We don't have data about for millions spanning over millions of years in the past, so we don't have continuous curves, but we have discrete data that we use. Did everyone hear me?
Yeah. So second question is now again from Mr. Furqan Hamid. He is asking, all of earthquake data is taken from research in USA. Can we use it for Pakistan, as rocks may be different in two regions?
So first of all, not all of the data is taken from the US. There are European programs where they have installed hundreds of seismometers all across the European continent. Secondly, where the state of practice international exists right now is we call it the ergodic assumption. Basically, what the ergodic assumption is, the attenuation functions would be identical whether they are developed for California or they are developed for Pakistan. So basically, the assumption is that the rocks, I understand that they're different, and ideally we need a lot more data to get the differences in the rocks forms. But right now we assume that if we get the data from one continent, it is applicable to all the different continents of the world, and this assumption is called the ergodic assumption.
Okay, nice. Now, the third question is again from Mr. Furqan Hamid. He is asking, which waves are taken into consideration for design, P waves or S waves?
The S waves are basically the ones that cause most of the destruction. But I think there are three types of waves. The body waves, which are or the surface waves. Most of on the ground is due to the surface waves. And there are two types of surface waves: the relay waves and the love waves. And the rolling waves. So most of the destruction is caused by the relay waves and the surface and the rolling waves. So it's not the S waves. It is basically the love waves and the rolling waves that cause the destruction.
Sir, we have another question from Mr. Muhammad Imran. Now he's asking why the dowel bars should be bent or extend inward rather than outward into the concrete footing for seismic areas.
Most of it, most of the detailing, and I think Rizwan Sahab is also listening, so he'll be a better authority than me on this. But most of the detailing that is recommended is based on empirical, tests, and it basically we would like this. I don't recall we have to bend it inwards only, but even if we are bending it inwards, basically it is because the core remains intact more longer as compared to if the cyclic column excitation going on. But I am basically not right now. I'm not able to answer this. Maybe Rizwan Sahab, can you help me in this? सर आपकी आवाज नहीं आ रही अब आ रही है
Rizwan, can you come on the mic?
I'll be surprised if this is a real consideration because it has been a while since I have checked the detailing requirements. Mostly the draftsmen do it. I don't remember it part of any seismic code. And correct me if I am wrong.
Okay. Can you hear me now?
Hear you, Ji.
Okay, can you hear me now? Hello?
दो mics होंगे एक mic तो off करते हैं all right so maybe the concept can answer this so
जी रिजवान बात करें आप
The answer is
वो म्यूट कर रहे हैं वो लीव करते हैं
yes, the answer is that this is not a requirement specific to seismic zones. It's a general requirement. I hope that the vertical column bars as they get into the foundation. If you look at the internal equilibrium of the joint would not be in equilibrium if you look at the struts and ties formed within the joint if the bars are bent outwards. So, in my humble opinion, this is a general requirement for maintaining the internal equilibrium of joints. So, it is the correct practice to turn them inwards towards each other rather than away from each other, away from the column center.
I need to actually learn this but
Rizwan, can you mute your mic now, please? Dr. Saab, we have another question from Khurram Shahzad. He's asking, most of the buildings in Islamabad were designed according to seismic zone 2B. Construction stage now. Can these buildings will be redesigned according to zone 4? Seismic hazard analysis report of the project located in, and this question is basically is asking about 2B and if some buildings are not designed according to 2B, so what would be the situation?
The simple answer is that most of the buildings that are tall, most of the tall buildings in the blue area, I know for a fact that they're not designed on zone 2B. So, you know, the structural designers simply didn't trust a Pakistan building code while designing those buildings. The second question is what needs to be done if they are not designed as per zone 4?
join without cookie.
Okay, so the simple answer is San Francisco Hall of Fame was many of the tall buildings were constructed in 1970s. Those buildings are not even closely, remotely, able to resist the San Andreas fault shaking. And what they did was they retrofitted those buildings. So yes, retrofitting needs to be done, but not. It's not because this Islamabad, but most of the buildings, the tall buildings that I see, in Blue area were constructed by international consultants, and they didn't use Zone 2B to build those buildings.
Now, question from an unknown participant. His name is OPPO nickname, so I don't know what is his real name. Anyhow, we have asked, sir, most buildings in ISL have been designed as per Zone 2. Now, what are the retrofitting methods available to make these buildings safe? ISL, I think he means Islamabad. I think
Yes.
you have already answered the question. So,
Yeah, but
now this question is from Khurram Shahzad, and he's asking, Seismic Hazard Analysis report of the project located in Islamabad. The value G is 0.41. I don't know whether this is a comment or a question.
well, Islamabad, as per Building Code of Pakistan, is in Zone 2B, and for Zone 2B, the PGA is 0.2. So it's not 0.4.
Yasir Mahmood Saab, you are most welcome. A question
Okay,
on my.
a lot. Okay, I have two questions. The first one is that under which condition do you consider that we should design the building as per near field earthquake or the far field earthquake? Where do we find it from the code?
Well, ASCE 716 says if the building is located within 15 kilometers or probably 25 kilometers, then you classify it as the near field. You classify it to be near the earthquake source. The repercussion of that is number one, directionality or orthogonality of the of the ground motions history. And the pulse like the pulse, we have to consider the pulse like excitation of the foundations.
Okay, sir, I understand that one, but the problem is that there could be different buildings. For example, there could be short building and there could be tall buildings, right? And if there's any near source, right, there is a chance because of the natural period, the tall building might not be affected by that source, because the tall building, they have a longer time period, right? They have a longer natural period.
I can now hear you. बताएं यासिर, अब बोलें.
Yeah, sir, my concern is that if you have two buildings, right, one of them is like maybe 5-story building and the other one is like 15-story building, right? Both of those buildings are going to have different time periods, right? Now we understand that the far field earthquakes and the near far field earthquakes, they have different time periods as well, right? So both of the buildings in the same region are not going to be affected in the same manner from the near field earthquake and far field earthquake. So how do we identify under which condition should we design the building?
Well, the smaller buildings are more susceptible near the source because high frequency content from the source is more as compared to buildings that are far away. Taller buildings are more susceptible if they're far away because most of the high frequency content tends to as the waves pass through a lot of ground. So, taller buildings are more susceptible, but more than that, I think the type of soil on which the building rests is more important as compared to this effect. This effect, whereas it exists, and people understand that this effect exists, but I don't know of any literature that has quantified the effect of high frequency content on, for example, stockier buildings as compared to longer buildings because they are located near the fault or near the source.
Okay, Okay, I got that. And the next one, since you mentioned the soil, under which condition do we ignore the soil structure interaction?
Well, I was going through NEAS. NEAS is NEES. You guys can search it. They provide a lot of free publications. The Electronic Building Initiative, which is the Bible for the performance-based engineering, and the PEER, TBI, both discourage structural engineers to basically engage into soil structural interaction at this stage. So I'm talking to you about. I'm actually communicating to you something that exists in books that are considered to be fundamental for the performance-based approach. As far as the typical, the conventional approach is concerned, I think structural engineers should not engage themselves into the soil structure interaction at all, because even if the more advanced forms of the publications tell us that they discourage engineers to engage into that, I would not recommend right now that you should engage in soil structure interaction unless it's a very unconventional building.
Yasser Saab, are you done with it? Your mic is mute. Please unmute your
I'm
mic.
sorry. Okay, I'm sorry. I have one last question. You have mentioned two factors. There's FA and there's FV, right? Do these factors relate to the far field and the near field earthquake? No,
they relate to the stiffness of the soil on which it rests.
Okay. Thank you so much.
Thank you. Thank you very much. So we have now questions on the text, Dr. Saab. This is from Manal. The question is, are plinth beams necessary to provide at ground level? Is there any compulsion given in any seismic code to provide plinth beams? If no plinth beams, then should we have to tie the footings or isolate footings? Can also used no tie at plinth level and footing level. I hope you have understood there is something wrong with the grammar. So
no, I understand that completely. Yes, it is a requirement of the building codes. I don't remember the exact provision right now, but I'm sure it is IPC requirement to tie all of the independent foundations by using beams or die beams or something. So you have to do it for earthquake-prone regions, and I don't know of any building that we did without it. So yes, you have to do it. As per I think IBC QB condition or UBC can be. I don't remember the exact provision. I can get back to you on that one.
There is some noise in the background. Anyhow, Dr. Saab, the question is, can you please, this is from Usman Ilyas, can you please explain that shear wall is a retrofit strategy or not?
Sorry, the shear wall is a?
Shear wall is a retrofit strategy or not?
It might or it might not be. Shear wall can definitely hold part of the structure, but so the exact retrofitting strategy depends on the state of the building after you analyze it. Yeah, that's. So exact retrofitting strategy is basically it depends on the exact form, the analysis of the building. You know, after you analyze the building, you see what the effect of the building, what the weaknesses of the building are. If for example, is a punching shear type of area susceptible in the building, shear wall won't have. So short answer is might or might not be.
Next question, Dr. Saab, is from Mr. Ilyas Niazi. He's asking, can we provide flat slab in Islamabad?
No. I think I'm sure that the UBC prohibits provision of flat slabs in zone 4. I would, but since it's zone 2B, people have designed flat slab systems. I don't consider Islamabad to be zone 2B. I consider it to be zone 3 or 4. I won't do it.
Right. Now, this is again a question from Manal. Modeling foundation in E tabs together with the building in model is better, or separate foundation is safe? I think you want to speak about this in the beginning of the
I talked about it very briefly. I'm mostly out of energy today, so I talked about it very briefly at the start of the lecture. Most of these young structural engineers, when I see their structures done, they make they separate the finite element model of the foundation from the finite element model of the superstructure, and that is wrong. And the reason why it's wrong is because if you look into the deflections, if you use fixed supports to model the base of the building, basically what you're saying is that none of my foundations will deflect. And then you are calculating all of the forces in the basement floor or the first floor above the supports. That might be very different, you know, if you have a flexible raft, and frankly, we had I had a very literal conversation about this with a few of our experts. We can have flexible rafts. If you have a flexible raft or if other flexible foundation systems, the distribution of forces in the floor above the foundations can be significantly different as compared to if you have fixed them or pinned them, you know. So please don't make this mistake. Model the foundation with the superstructure so that you can take into account the effect of variable deformations of the different supports in the superstructure. You cannot isolate the two models and then claim that your force distribution or force redistribution in the superstructure is as per your deflections in the foundation.
We have another question from this is just from Ilyas Niazi. He's asking, ASCE 7-16 allows you can model superstructure separately.
I don't think so. First of all, and number two is ASCE 716 is written for different audiences. Some of those audiences are, you know, some of those audiences are very starting level audiences. So structural engineer who's just starting to design, the ASCE 716 is written for that. And ASCE 716 is also written for the very high-end professionals where you can engage into soil structure interactions and the effect of amplification of the ground motion on the effect of soil on the ground motion amplification and all that. So the question is, no, I don't think so. How can you? I don't agree. I don't think ASCE 716 allows that, and We can have, I know Ilyas very well, so we can have a conversation about that later.
Sir, we have a question from Mr. Yasir Mahmood. He's asking how often the seismic maps are updated since the earthquake intensities keep on changing with time. For instance, previously Malaysia was not considered to be affected by earthquakes, but now because of earthquakes from Indonesia, they have started designing buildings for the earthquakes.
Well, so there was ASCE 716, then there is ASCE 710. So every 6 years, they do look at the seismic hazard maps. In the US, they have even started they have stopped looking at the codes for seismic hazard analysis of the buildings. What they do is they engage into a practice called site-specific seismic hazard analysis. That practice involves using probabilistic seismic hazard analysis done by geotechnical or geological engineers. And what those guys do is they calculate the SA and SS for considering all the soil effects for the project at hand. So in that case, every time that is geotechnical or a geological engineer is doing that, he is calculating or he's relooking at those provisions. But for general public, they do have a relook at that on average every 5 to 6 years. There are programs, the research programs in Europe and in the US, and both of those research programs basically are geared towards assimilating the data and relooking at all of this work that we have done. So it is evolving constantly, and at the codal level, it's probably 5 to 6 years.
Next is Mr. Ilyas Niazi. You have raised your hand and you have sent a question by text also. So what do you prefer? Would you like to come on the mic or should I read your question?
Excuse me, sir, can you hear me?
Yes, go ahead.
Sir, my question, is it economical to provide a dual system for 10 to 12 stories? Because mostly in Pakistan, 10 to 12 stories are preferring dual system these days. I don't think so, but I just want to listen from you people.
Well, dual systems are dual systems are really good when it comes to certain height of the building, and that basically is due to the fact that if your shear wall is loading your top floors as it happens more often than not, then you would probably like to terminate your shear wall at a certain height. It depends on the the footprint area of the building also. Sometimes the building has a big footprint area and you might not like to use the shear walls, but you don't have any other option if you are controlling drifts for a slender building. The dual system might be the only system that is left for you to control the drifts in the lower stories, especially.
Thank you, sir.
All right.
Now we are almost now over with the question answer session, but last question we have from Muhammad Imran, and he's asking, what is the boundary limit? What is the boundary element in shear wall?
The boundary elements basically आप लोग जो properties use कर रहे हैं concrete की, that is most of you probably know already. If you confine concrete, the ductility and its strength increases. So boundary elements are nothing but what they want you to do is they want to confine it more as compared to the other parts of the shear wall. So they want you to confine the edges of the shear wall more as compared to the other parts of the shear wall. And the reason that they want to do this is because they want to give more ductility to the system, meaning that your building can sustain a lot of interstory drift without being without failure. So to do that, you already know that at the edges of the shear wall, there is a lot of strain, because plane sections remain plane. Well, it's a poor assumption to have, but it's still valid to some extent in case of shear walls. So to counteract those axial strains that are high in the boundary regions, they provide those they mandate that you provide those closely spaced stirrups and all of those things to confine the concrete better, so that it can continue to resist compressive stress, compressive. It can continue to resist applied load much farther than 0.003, much higher, at a much higher strain rate.
Well, we are already hard pressed with the time, but since the discussion and the quality of questions is forcing me.
And I do apologize. I do lack a lot of energy today. I feel like not speaking because I've been, we have a rush of projects here, and I was awake till 2, probably 3, and didn't sleep much last night.
So you're doing a good job. You have done very well. Now, last question, please. I won't entertain any further questions.
No, let them come. I'm enjoying the question, so I'm okay.
This is what I was also enjoying. This is why I am going ahead. I mean, we have already, the limit is already exhausted, but I'm going ahead. So this question is from Umair Afzal. He's asking, what will be effect on cost if we design a building in northern areas as per IBC, because we will be on more safer side instead of using Pakistan building code?
Well, the short answer is that there will be some increase in cost, but don't expect that the cost will be exorbitantly high as compared to if you design it in UBC 97. I think what most of the structural engineers need to do is they need to educate the clients. When we are in the practice, we are competing with each other, and some of us would like to take business away from others by promising a more economical building and telling the client that it's legal. The cost of designing the correct building is higher, but it is not as high as you would think, because we do the rate analysis, or the I'm also heading the costing section nowadays. So I know that for a fact that a story high of shear walls is approximately, it costs not more than 1 million rupees. You multiply it with 12, it will cost 12 million or maybe less. So that cost is probably less than the cost of putting tiles in the building, if you count the cost of finishing. See, so it's not exorbitantly high, but as structural engineers, I say that people say that doctors are responsible for the lives of the patients. Well, you guys, what you guys are designing, you are also responsible for a lot of lives, and you should take it very seriously. So if there is a slight amount of cost that you guys have to pay, that your client has to pay for doing something correctly, I think you should do it.
So Dr. Saab, now we have no further questions and nobody has raised any hand now. So we conclude this question and answer session. Dr. Saab, Pakistan Society of Civil Engineers, privileged and honored to have a speaker of your stature on our platform, and the lecture you have given today was marvelous, very fascinating, very knowledgeable, and the questions, the quality of questions which have been asked, they speak the quality of your lecture. Thank you very much, and we know you are a very busy person, and thank you from the depth of our heart. That's the time. And I'm also
I'd like to thank all the audience. Apologize to the audience a little bit. I frankly didn't have the time to prepare. I just going through the slides that I prepared for the last year. And so thank you very much. I wish all of you the best.
Thank you, Dr. Saab. Just bear with me, few points. Rizwan, thank you very much for your input today. And we are also honored to thank our professor, Mia Ziauddin Sahab, for watching this lecture. Thank you, sir, for being a participant. Thank you very much. And all the participants who are here today, thank you very much for coming and supporting the cause for which PSCE has been established. I would like to thank, on behalf of PSCE, all the audience who have listened to this lecture live on Facebook. Today we did not had a transmission on YouTube, it was only Facebook. And we are again so all the viewers who have watched this lecture on Facebook, thank you very much. I know that there were a few people from Europe, and I think today we had somebody from India also. So thank you very much for participating in this lecture. And now a few announcements. One, regarding the quality of the transmission. Yes, I have noted some text messages that people were having difficulty in the audio, as well as some breakage was taking place in the audio. Now, as far as I am concerned, we have our technical people present here in the background. I am also monitoring the sound and quality. What we were receiving from Dr. Saab was perfectly good. So now what you people were receiving is because of the net speed at your end. I hope you people know that for Zoom, you need a minimum speed of 2 MB to have a quality transmission in which there will be no breakage of the audio, and you can listen the lecture very smoothly if you have a 2 MB speed. 1 MB will also do, but again, if it is less than 2 MB, then there will be some distortion. So please try to have a net speed of minimum 2 MB, then you can enjoy the lecture more in a better way. Now, regarding, I am very pleased to announce on behalf of PSC that we have opened our first overseas chapter, that is in Kingdom of Saudi Arabia. It is being headed by engineer Hamid Ismail, who is working in Saudi Arabia with a private company. And Alhamdulillah, this is the first development in as far as overseas chapter is concerned. So once this chapter is successful, then we will again expand ourselves in other countries. Regarding our membership as associates, we have 158 to date. Magazines are 8, and newsletters already issued are 10. Now, regarding next lecture, it will be delivered by Dr. Fawad Najam, who is a professor in NUST, and his topic is Scope of Performance-Based Seismic Design of Structures in Pakistan. It will take place on 14th of November, same time, and it will be a webinar. Still, we have no plans to start live lectures with the flesh and blood audience because we are hearing that a second spike of COVID-19 is going to come. So we are being careful more for your health, for your safety. So the webinars will continue. At least the next lecture will be on webinar. So thank you very much. The certificates will be available from the office, which last time I told you that was 32 Main Gulberg, Lahore. And anyone who wants the certificates to be delivered by post, by courier, kindly deposit 200 rupees in our account. Account number who is with Miss Sadia Naveed. She will, you can contact her on telephone or by email. And in fact, she will tell you she will announce the account number on Facebook and by email to everyone. So she's telling me, correcting me, it is 300, not rupees 200. 300 you have to deposit if you want it by courier. Otherwise, you have to collect it yourselves from our office. And I don't think there is anything else. So 14th November, Dr. Fawad Najam would be here to give the lecture on the scope of performance-based seismic design of structures in Pakistan. So we are talking about earthquake today, and inshallah next time we'll again talk about earthquake. So stay safe and take care of yourselves. God bless you all. I will see you on 14th of November. Thank you, Ji. The shield, Dr. Saab, one last thing. Your shield and your certificate, inshallah, you will receive by post that from Pakistan Society. Thank you very much.